let's finish mechanism. So we talked about mechanism, and we said mechanism is basically the path that the reaction takes. So we see the final product, but how did they get there? It is the path of the reaction. What was the process? What had to happen for us to see the final product? So far, so good. Okay, now the last one, I'm actually going to show you doing a practice problem. So here I have a proposed mechanism. These are the two reactions. Now, let's figure out what is the net reaction. Okay, let's figure out the net reaction. And the best way to teach is to do practice problem. So if I'm going to add up these two reactions together. You add it up with me. Now, when you add up the reaction, you need to cancel out the ones that show up on both sides and exactly the same. Is there anything I can cancel out? Shows up on both sides is exactly the same? Yeah, the NO3. I can cancel out the NO3. Is there anything else I can cancel out? Not really. Okay, so then I'm going to add up these two reactions. If I do that, I get 2NO plus O2 going to 2NO2. Now, before you get confused, where did I get 2NO from? I have 1NO, I have 2NO. So I just combine this together to make it more cleaner. So it will be 2NO plus O2 going to 2NO2. So far so good. I add up this reaction to get my net reaction. Now, is there any intermediate in this mechanism? What's the intermediate? Tell me. The intermediate is NO3. It gets crossed out. Also, intermediate is the atom, the compound that does not show up in the final product. It gets formed and it gets used in the process. It gets formed and it gets used in the process. It does not show up in the final product. So far, so good? Okay. Now, if I want to come up with R theoretical, I want to figure out R theoretical based on the mechanism. I want to figure out R theoretical based on the mechanism. Okay, we talked about that last time. So what I'm going to do is going to be R equal. And remember what we talked about. We said that the R theoretical is going to be based on what? Based on the rate determining step, right? It's going to depend on the rate determining step. What is my rate determining step? This one, the slow step, is my RDS. You guys are following me that? So the slow step is my rate determining step. So the R theoretical is going to be just based on the slow step. And the reason for that is the slow step is going to take most of the time to happen. It has a huge hump. Once you get over that, once you get over the hump, and once you make this product, then the fast one is just whoosh gonna happen. It's gonna be very fast. So that's why the rate is only based on the slow step, because this is where the trouble begins. This is where it's going to take longer to happen. Once we get over this, the next step is really, really fast. Okay, so this is my rate determining step, the slowest step. So I'm going to write the rate law based on this elementary step. So it's going to be equal K2, that's the equilibrium constant, times NO concentration times NO3 concentration. You guys are good? Okay. Again, it's a rate law, rate constant times the concentration of the reactant. I have NO and I have NO2 and NO3. And we also said that if you're using an elementary step like we are here, the coefficient can be the order. The coefficient can be the order. So far, so good? Okay, so this is what we learned last time, and this is great. Hopefully you got this. There is one problem with this. There is one problem with this. I want you to look at this and see if you can see what the problem is. okay, here's the problem. Here's what I came up with. This is my rate law. The problem is, when I look at this rate law, and this is my main reaction, there is no NO3 in my main reaction, is there? So I can't have this because my net reaction is my final product. This is my final reaction. And the rate law that I have based on the mechanism has NO3. But NO3 is not in the net reaction. Now, because NO3 is not in the net reaction, I cannot measure it in the experiment. You know how to figure out the rate law for this and to confirm that this is the right one? We have to do experiment. Well, we can measure an intermediate in the experiment. So this is not going to work out because this one is not in the net reaction, so we can't measure it in the experiment. So what are we going to do? What we have to do, we have to sub for this. What we have to do, we have to sub for this. So this is a problem because this does not show up in my net reaction. So we have to sub for this. Okay? So I'm going to go step by step to show you how we sub for it. It's actually not that bad. I want you to look at step 1. Step 1 is an equilibrium reaction. It goes forward and it goes backward. Okay? So the reaction, there's a forward reaction, there's a backward reaction. We call that equilibrium. There's a forward, there's a backward reaction. Okay? So let's go over here. So step 1 is my fast reaction. And I have an equilibrium. And what equilibrium means, it means the rate of the forward reaction equals the rate of the backward reaction. So far so good? Okay, because I have an equilibrium going on. Alright, now what I'm going to do, I'm going to write the rate law. I'm going to write the rate law for the forward reaction, and I'm going to write the rate law for the backward reaction. I'm going to have K1 times concentration of NO times concentration of O2 equals K minus 1 times concentration of NO3. I'm going to explain this to make sure you're not lost. So I just wrote a rate law for this elementary step. The forward reaction would be concentration of NO times concentration of O2. Now, the backward reaction, this would be this would be the reactant, so it would be the concentration of NO3. So I did that over here. Now, when we have an equilibrium, at equilibrium, the rate forward equals the rate backward. So I equal these two to each other. So far, so good? Okay. Now what we're going to do, we're just going to do some, not really fancy, but cool algebra. What we want to do, we want to isolate NO3 because we want to isolate it so we can sub it later. We're going to isolate NO3. So I'm going to move things around so I can isolate NO3. If I do that, K1 over K minus 1 times NO times O2 is going to be equal NO3. So all I did, I just moved this over here to isolate NO3. You guys are good so far? Okay, this is not bad. Now, because I just isolated NO3, I can sub this into the rate law equation. I can sub this in a rate law equation because it's come back here. This was my rate law equation. The problem was NO3. Now I'm going to sub this out. So let me rewrite that equation. That was R equal, let me write it a little bit higher up so I can, that was R equal K2 times NO times NO3. Now, all I'm going to do, again, I'm going to sub this out. what am I going to do? Instead of having NO3, I'm going to plug this one in. So I'm going to sub this out. Instead of having NO3, I'm going to sub this one out because I isolated this whole thing equals NO3. Yeah? Okay. Hopefully you found me so far. So now, what that means is R is going to equal K2 times NO. Now, instead of writing NO3 concentration, I'm going to write this one out. Times K1 over K minus 1 times NO times O2. Yeah? Okay, we subbed it out. Now what I'm going to do, I'm going to clean it up. I'm not doing anything fancy at all. I'm just going to clean it up. Okay? To clean it up, I'm going to move things around to clean it up. So technically what I have K1 in there times K2 over K minus 1 times NO to the power of 2 times O2. I want to show you how I clean this up. So I just put all the K's together. So K1 times K2 divided by K minus 1, nothing new. I have 1 NO, I have 2 NO, so NO to the power of 2 and then times O2. You got so good so far? Okay. Now what I can do, I can cancel out the K. These two K can be canceled out. So if I do that, so I cleaned it up even more, then what I have K times NO to the power of 2 times O2. Can we write it 2 here? So far so good? Okay. So now I cleaned it up. Okay. So now what does that mean? That means my rate is going to equal K2 times NO to the power of 2 times O2 to the power of 1. This is my rate law. So far so good? Okay. And this is good because we have NO and we have O2 in the main reaction, right? That means NO is going to be second order and O2 is going to be the first order. Now what do we have to do? We have to look up the R experiment. Actually do the experiment and then compare it to the rate constant based on the experiment. Because, I want to repeat it one more time and make sure you really understand it. The rate constant that we just got, this is a rate constant based on the mechanism. Now what I'm going to do, I'm actually going to do the experiment, get a rate constant based on the experiment and see if they matched up. Now I actually looked it up and I noticed that this actually matches our experiment. A rate law for if we do the experiment. Now what does that mean? When the rate law based on the mechanism matches the rate law that you get based on experiment, the experimental one, that means that this was a good mechanism. Our mechanism was right. That's why we end up getting this same rate law. Yeah? Okay. I know this was a little crazy. You want to do a practice problem? Yeah? Let's do a practice problem so it looks a little bit less crazy. Just a little bit. Let's do this. You got this. So, I have a reaction. 2NO plus Br2 going to 2NOBr. Is this a one-step reaction, you think? No chance. I mean, maybe. But the chances of this being a one-step reaction is really, really low because I have 3 molecules here. This would be a trimolecular. And trimolecular is really, rare. Do you agree? So would this be a one-step reaction? Probably no, because I have a tri-molecular reaction. Where the tri-molecular comes from, I have 2 of these and I have 1 of these. I have 3 molecules that have to collide at the right time, at the right orientation, have enough energy for this reaction to happen. That is asking way too much. Tri-molecular is very, very rare. We're good? So the chances of them being one step, not very highly, because tri-molecular is pretty rare, because you have to have 3 molecules, 2 NO and 1 Br, collide at the right angle, at the right time, and then have enough energy for this to happen. So possibly no. Now, we want possible mechanism for this, okay? And here's one of the mechanism that we're going to go over. Here's one possible mechanism. One possible mechanism is I have NO plus Br2 going back and forth to K minus 1, NO-Br2, and then the second step is NO-Br2 plus NO going to 2 NO-Br. Now, the first reaction is my fast step. The second step is my slow step. You get that good so far? Okay. So, this is my reaction. It's probably not going to happen in one step. It's probably because it's tri-molecular. There's no way everything is going to happen with 3 molecules. Possible, but very rare. This is a possible mechanism. Okay? This is a possible mechanism. I don't like it that I highlight this. Let me erase that. It looks a little messy. Okay. This is a possible mechanism. Okay. Now, the first thing that I want you to do is write the net reaction. Convince yourself that if we add up these 2, this is what we get. Don't ever take my word. Don't trust me. Yeah. Add up these 2 and convince yourself that you are going to get the same net reaction. When we do that, we have to cross out the we cross out the one that gets cancelled out. Which ones will get cancelled out? They have to look exactly the same on both sides. It would be NO-Br2. You see it? They look exactly the same on both sides, so we can cross it out. Anything else we can cross out? What do you think? Anything else we can cross out? Not really. Okay. So now I'm going to add up these 2 reactions to write the net reaction. I have 1 NO. I have 1 NO. So I have 2 NO. So I'm going to add 2 NO plus Br goes to 2 NO-Br. Okay. Is this the same reaction on top? Yes, it is. Happy face. Yes. So yes, if I add up these 2 reactions, I get my main reaction. First part is out. We got it? What is the intermediate? What's the intermediate in this reaction? Is NO-Br2. NO-Br2 is an intermediate. You guys agree? Okay. So I'm going to write that down too. So NO-Br2 is my intermediate. And again, one more time, intermediate is something that it does not show up in my final equation. It does not show up in my final equation. Okay. What do we have to do next? Now, what we want to do next, we want to write a rate based on the mechanism. Okay? We want to write a rate based on the mechanism. Okay? We've done this before. When we want to write a rate law based on a mechanism, which step do we have to look at? We have to look at the rate determining step. And the rate determining step is the slow step, which is the step 2 in this case. So this step is my rate determining step. And when we do the rate law based on the mechanism, this slow step is my rate determining step, because you are as good as your weakest link, right? And once you get over the hump and this reaction happens, the rest will happen much faster. Okay, so now what I'm going to do, I'm going to write a rate law based on the mechanism. That would be my second step, my slow step. So it would be K2 times concentration of NOBr2 times concentration of NO. Okay, NOBr2 times concentration of NO. And we talked about it. Since this is an elementary step, it's okay to use the coefficient. It's okay to use the coefficient, right? It's okay to use the coefficient. Again, why is it okay to use the coefficient? Because this is an elementary step, right? In an elementary step, it's okay to use a coefficient. I know I'm like repeating myself, but I want to make sure you really understand that. Now, what do you think the problem is? We do have a problem. The problem is over here. This is an intermediate. This was our intermediate. This does not show up in my final reaction. This is not in my final reaction. If this is not in my final reaction, I cannot measure it if I do experiment to compare to the rate law for the mechanism. So this doesn't show up in the net reaction. So I need to solve it out because it doesn't show up in my final reaction. All of these have to be in the final reaction. Okay? All right. So what I need to do, I need to sub it out. You already know that. We need to sub for this. We need to sub for this. Okay. How am I going to do this? We're going to write the rate law for the step 1 reaction. Okay. We want to write the rate law for this step. Now this step, for the fast step. And this, because we already wrote that one for this one. So you want to write the rate law for step 1. We already wrote it for step 2. Now, the fast step is equilibrium. It has a forward reaction and it has a backward reaction, right? Okay, we will get into equilibrium more later. Now, so the rate forward equals the rate backward because it's an equilibrium reaction. You have a forward reaction and you have a reverse reaction. And the rate of the forward and the rate is coming back, they equal each other. So I'm going to write the rate constant for the rate forward. K is equal concentration of NO times concentration of Br2 equal for the backward K minus 1 times concentration of NOBr2. Again, all I'm doing, you know how to do this. For the rate law, concentration of reactant, elementary step, I can use the coefficient. For the backward, again, concentration of the reactant. Okay, nothing fancy whatsoever. Now what we're going to do, we are going to solve or isolate the intermediate. Solve for the intermediate. Okay, so I'm going to isolate the intermediate. I want to move this one to the other side. Move it to the other side so I can isolate the intermediate. It will be K1 over K minus 1 times NO times Br2 equals NOBr2. You following me so far? Okay. Now what am I going to do? Now remember my rate for the rate determinant step. My rate was K2 times NOBr2 times NO. I'm just rewriting my rate law based on the rate determinant step. Okay. Now what I'm going to do, you can probably guess, what I'm going to do, I'm going to sub this out for this one over here. Okay, because all of this would equal that. So I'm just going to sub it out for that. Again, nothing you had never seen before. You guys agree with that? Okay. So let's do this. If I sub it out, what I'm going to get, I'm going to get rate. Give me 1 second. I'm going to get rate is equal K2 times K1 over K minus 1 times NO times Br2 times NO. You guys follow that? Okay. Now, I kind of subbed it and cleaned it up a little bit at the same time, so hopefully I didn't lose anyone. So I'm going to go over it to make sure I didn't lose anyone. So I have the K2 here, that's part of the equation. I have the NO, that's part of this equation. Now I had to sub this. This is over here. Is BR is NO and then K1 over K minus 1. Okay. Now, the same as before, we're going to clean it up. We're going to clean it up. Okay. If we clean it up, I'm going to get rate equal, because when I clean it up, I can cancel these out, okay? And then when I clean it up, I can also combine those two together, okay? So the rate is going to equal K2 times NO to the power of 2 times BR2. I know I'm going really slow. Sorry if you're a little bored. Don't fast forward. Just keep listening to me. Yeah, not too bad, okay? Not too bad. So now this was my rate determining step. I got my rate determining step. Now it's good since I subbed it. It has NO to the power of 2, BR to the power of 1. So if I go to my main reaction, that means NO was a second order reaction and BR was a first order reaction. Now what am I going to do? Now I have one. Is great. There's no intermediate here. All right, tell me. I know you know this. How would you check to make sure that this mechanism that we proposed is good? What you're going to do, now you're going to go to lab, you're going to do experiment, okay? You're going to go to lab and you're going to do experiment. And you're going to do experiment to figure out what is the experimental rate law for this. And I actually looked it up, and the R experimental does match. It matches the R theoretical. And when the R experimental matches the R theoretical, we are good. That means that was a good proposed mechanism. Yes? Okay, hopefully you're not fried. Hopefully you got this down. All right, nice job. Really, really nice job. We are almost done. There's like one really easy thing to talk about, and I want to do a little bit probably more practice problem. But beautiful job. I will talk to you guys next time. Hopefully you got the mechanism down.